Until then. He's getting like 60, 65 a year right now. He's doing pretty well. And Taylorsville, there's nothing in Taylorsville. But land. People own land. So he's gonna be okay. Man's gonna buy a dog, have a whole happy family. I'm just gonna have my cubicle. Maybe a coffee mug or two. Not gonna dip into it too much.
Slideshow from current. Okay, morning everybody. I hope everybody is doing well for the homeworks. I know it's going to be a challenge, and try your best to finish this by early next week. Okay, so because I was planning to chat about this. Once everybody submitted, we can chat about answers. So today's lecture is going to be a little bit shorter because I don't want to disclose all the answers to you yet. So we're going to discuss about homework next Tuesday. Then we can shift a little bit things. I'll pull what I was intent to talk about next Tuesday today. So we basically going to also have a quick summary about the whole portion 1 because we just finished everything. We will do a quick review, spend about 20 minutes or so. I'll talk about what are the key concepts everybody need to understand. I'll give you some guidance how to prepare for the exam. Although for me, you should never study for the exam. That should be part of your knowledge. Anyway, the exam we already talked about. It's going to be roughly 10 days from now, right? Not the next Tuesday, but the Tuesday after next week, okay? And the format, it will be, we're going to do a mixture of concept answers. So like we did for the quiz, understand the key concept. We'll have multiple choices. We will have a few numerical questions. Numerical question need a little bit of math to understand how you can use the knowledge learned in class to understand the size scale of polymer. And we can chat more. So Tuesday we're going to review the homework. So make sure you send in before 8 a.m. We begin the lecture for the homework, okay? Then Thursday we're going to have probably either we can take a pause, let everybody study, or we can just move on to the next chapter, talk about polymer solution. Okay? So I'll see how everybody's homework, then decide how to do that. We have the third homework also assigned, so make sure you take a look at that. So let's finish something we left. We talked a little bit about the scales concept, like scaling concept, how we can understand how polymer behaves a different scaling relationship. Move the chair a bit away. Specific what we mean is, oops, let me make sure nobody get hurt. Yeah.
Are you all right?
All right. That's fine. It's okay. Nothing bad. It's just a small car with some luggage fell over. Okay, so when we were left last class, I asked everybody to think about a couple cases. We talked about how does RG with respect to degree of polymerization, or how does it grow with molecular weight, right? So we talked about a few cases. This is for ideal chain, as we know. you would grow, the size would grow with molecular weight power of half. And this is true for all kind of model we talk about. Free joint chain model, free rotation chain model, and hindered rotation chain model. Okay, so we also talked about in good solvents how this will now become 0.6. This factor is bigger and has stronger dependence. We're going to actually cover a little bit later today to explain how this is going from 0.5 to 0.6. So this is a real chain in good solvent. This will be anything you touch, anything you play, anything you work with. Most of the polymer are actually processed in good solvent, so that's a good relationship to know. We also talked about last scenario is when you have a polymer was in a bad solvent. We will ask everybody to guess what the connection between the molecular weight and radius. Anyone has give it a try? Okay, so let's think about this. So this in a bad solvent, we should interpret as polymer as a globular or basically a collapsed coil. A collapsed coil will behave like what? A solid piece of rubber ball. You know these bounce ball? When you were little, you might be amazed how you can throw a ball bounce to the ceiling. My little one is very amazed. So that's exactly ideal you want to link to. So in that case, how heavy your ball is dependent on the volume, right? So as you can see, your molecular weight is directly transmitted to the mass because the longer the linear molecular weight increase, you're going to have an increase in the mass. If you have a spherical structure, you would have mass would be proportional to the volume. So in here, radius of a solid ball, those are not exactly one-to-one, but they're proportional. So in this case, we can see this is a power of 3 dependence. Mass is n to the power 1. So in this case, then we can infer the radius and the mass or the molecular weight will be the 1/3 of relationship, right? So you need to increase mass 3-folds to increase power of 3 times to increase the Rg twice. In other words, radius need to be, mass need to be a factor of 8 to have a twice increase in Rg. Okay, so in this case, Rg is most strongly dependent on molecular weight. This is Leslie Wheat. Okay, so you need 4 times to have an increased Rg. This will be small, a little bit smaller than 4. All right, everybody following this part, right? So there's one last thing that we sort of chatted, but we haven't discussed too much detail is how about this 0.6 and how do we understand the real chain, where this prefactor is coming from? Something we know is that because of the moving away from idealized chain, so we will discuss a little bit how we get this value of 0. So moving away from idealized chain, we know we need to go from some conceptually idea of random walk to this is called self-avoiding walk, right? Self-avoiding, which is more representative to real chain. That means we are, in one case, random walk is some of the concept we use to get this. So can we use self-avoiding walk to get it? The answer is yes, but it's rather complex. If you're into computation, you're into modeling, then you can program such that you ask the program could never go back to the original spot, then tell me, run the simulation hundreds of times, get a statistical and end-to-end distance using that. That's how actually now modern days how people do. But imagine if this is not possible back into 50s, 60s, people already know this is the case. How do they do that? They can measure it, right? We know how to measure molecular weight. We know how to measure Rg. Then they can just measure it. You make the polymer, you throw into the tool, you measure the molecular weight, and you can plot it and understand it. So a lot of time people found more precisely is not 0.6, it's 0.589. I think that's the number. Okay, so it's closer to 0.6 we talked about, but it's a little bit slightly deviation. So it's prompted the physicist, someone, to think about why. How do we conceptually understand this particular interaction? And is there a simple way to explain? Let me open. Hey, come in. No problem. So, is there a simple way to understand what's the relationship and why we can arrive at this particular concept? It's actually pretty hard. How do we understand this? In good solvent, what is the size scale it will be equilibrated with, right? We cannot use a self-avoiding walk easily because it's rather complex without a computer. So again, the same person, P.J. Flory, was the one who came up with the idea, maybe there is a simple way we can understand this. And his idea is not hard to interpret. So this is a polymer chain. Ideal chain means you can overlap in the same place, right? But in not so idealized chain, your chain starts to expand to a bigger volume. So there's two consequences allowing this to be equilibrated. It's not infinity expanding, right? So what is allowed to expand it? What the force allowed to expand is expulsion force from your neighbor. Think about you are in a very, very busy subway. You're going to walk at 8 a.m., but this is the last train you could get on. It's full packed, but you're still trying to squeeze in so your boss don't matter you being late for 15 minutes waiting for the next one. You're trying to squeeze yourself in the door. But it's a finite size, train. You cannot squeeze as many as possible, right? We have a certain volume, we occupy a certain space. So that's exactly reason there's a repulsion force coming from the neighboring chain, inferring to the chain next to it. You can think about a bit subway. You're trying to squeeze in. That's a force coming from somewhere already occupying space. So using the very simple scaling relationship, we can imagine this will be proportional to how many number of repeating unit you have, the force of EXP expand. Let me find a little bit more space. Expand will be proportional to number of chain to what's the expulsion force will be proportional to density. This is the density. And we're using scaling relationship, so we don't worry about constants or any values in front of it. But this is just tell you expansion force will be, more chains you have, the more expansion force you're going to experience, the longer the chain. For a single coil, right? There's just more. If you have a shorter chain, so in this case, the length is smaller, so this will lower the expansion force you push for the other. This is talk about density. This is the mass, and it's basically proportional to mass divided by what? This is volume, right? So this is effectively is a density term. Okay, in this, so it's basically number of chains total to how many density of chain. So this gives you an idea how much forces you want to expand. How about the force to retain the shape? What forces control, say, my coil will not be pushed so far away from the coil?
Do you have any attractions among the chains?
Not exactly attraction, but close. There's another force is giving the attraction force. Any idea? I think I alluded to the last lecture when we talk about Gaussian distribution of your chain states. So if you recall that part, we talk about Gaussian distribution, how many chances of you distributing it. So that is directly relevant because when you pull the chain, you cannot pull it infinitely long. Why? Because there's retraction force coming from the entropic effect. So entropy don't want to make the chain long and straight. Entropy want to expand it, but it want to come back. So it's an entropic spring effect. So we know that is entropy holding. That's called entropic spring effect. So this is the effect actually holding the polymer chain together. Holding it together. Okay, I won't write all the detail, but you got the idea. And I think in the lecture note, I do have a short note on that. So let's take a look at this one. This is the case when you have idealized the chain, which in entropy is high because you have all kind of possible configuration. When you start to swell in a good solvent, not in this extreme, but when you expand, your number of density of states drops. And entropy is direct proportional to Boltzmann constant volume states. We know the entropic force will be exerted on your structure by a kT r squared by nb squared. And why there is this term? You remember in the Gaussian distribution states, we have basically dependence on r and nb squared. This is equilibrated states, and that's the end to how far you pull it away. So if you look at the equation, kT is a constant, kBT, Boltzmann constant. There's just a regular value. You can even omit that. T, when you fix the temperature, it's a constant. You don't need to worry about that. nb squared is what? Idealize the chain end-to-end distance. We know this will be the chain most happy. So when you start to pull it, you would have a force going to be starting applying retraction force. And it's proportional to r squared, which is end-to-end distance squared. So the bigger you pull, there's more retraction force you're going to be sensed by your chain. So now it's a very nice balance between entropic effect, which is going to hold it together, and expulsion force because of the, what is it called? The self-avoiding effect. You cannot occupy the same space. So eventually, those forces need to be balanced out with each other. And this is basically saying the total system energy, you can think about this expulsion, this entropic interaction. So can be generally described by this particular equation. And this is expulsion force, right? We already combined two n, so that's why it's n squared, r cubic. This is an entropic spring effect. We have r squared, depending on the size, and nb squared is free joint chain. If we take the first derivative, make it 0, this will arrive at derived by r, okay? So you would have a minus term here. R to the power of minus 3 will take a first derivative to r. You will have reaches minus 3, r power of minus 4. N is stay as is. Here, r squared first derivative will be equals 2 times r. And the system should have the lowest force. Now, if you remove this parts, you only consider this parts, you would reach, this is r to the power of fifths, combining together, will be equal or proportional to Vn2 multiplied by nb squared will be proportional to b squared n power 3. So now, you take a root 5 to here, you reach the conclusion or prediction the Flory had was r will depend on n power of 3/5. Okay, so that's why in the good solvents you have two factors competing each other. They're like having a tug of war. When they balance each out, it will happens to be radius will be slightly bigger than idealized chain. It's no longer n power of 0.5, but 0.6 in this case. Okay, we know the reason, right? If we expand two more, the repulsion force will not win over the entropic spring. Entropic spring will bring it back. If the other case, then it will push the chain as well slightly. So this theory also very simple. There's a few emitted factor. That's why the value is slightly higher than experimental value, but it's fairly good in a sense that it's easy to understand and easy to comprehend. So this theory also works for melt states. We talk about there are two special cases where your radius of gyration would be scaled with a molecular weight of 0.5. So your real polymer in the real world, even there's expulsion force, but should behave like idealized chain. I think I mentioned a couple times, and I'm just going to say one more time. So zeta solvent, so when you, zeta solvent is a little bit special. When you, in a good solvent, you're adding non-solvent. Your polymer solvent interaction going to drop. That's why you're adding some external force to push the coils to be smaller and smaller. The other way that Flory said we can have idealize the chain is in the melt. Yeah, melt is interesting. So he basically claims in the melt you could not tell since everybody is so close packed, right? In the melt, you basically have a polymer chain intertangled with another chain. So it's no longer a single chain where your neighbor is very far away. You know, if you like think about like big lots, you have neighbors several hundred meters away. In this case, you are no longer that far away. I even could hold on with another student to mimic that my polymer block is not necessarily intact with myself, but intact with another polymer chain. Like entangled pastile or something like that, you can imagine a picture-wise. So Flory says, in this scenario, polymer chain will receive, again, repulsion force and entropic force. But in this case, repulsion force is not centralized within the center of the molecule and pushing the chain outwards to expand. It will still have that force, but there's other enabling force is being applied to it. In other words, your neighbor chain is pushing as well. So if the chain cannot tell it's from myself or the other, then those two forces, expulsion force, basically cancels each other out. And if you only left with an entropic spring force, we know that force will be equilibrated when your coil is adopting a Gaussian coil phase. Effectively, your repulsion force from your neighbor and yourself, or who knows who is pushing who, cancel each other out in the melt states. Your chain ended up in idealized chain. Okay? in a Gaussian coil. So that's a special case. Actually, it's very hard to measure it. Historically, Flory said in the 70s, based on this equation, but nobody could do it. Right? Think about how people measure Rg in solution state is do light scattering for the polymer dissolved in solvent. The prerequisite you can do scattering is you need to have contrast. Imagine your polymer is wearing a red shirt, your solvent is blue, so you can see the red in the blue. It's different color. But if you have a polymer chain sitting inside the polymer matrix with itself, everywhere is blue because every polymer is blue. You can tell where the size and dimension of your individual coil. That's a problem. So nobody would be able to do light scattering for melt or X-ray scattering from the melt for polymer until in the late 70s or late 80s when neutron scattering was developed. And I won't go into detail, but simply saying if you apply deuteration chemistry, you replace a hydrogen with deuterium. They are similar sized, so you don't change the physical property as dramatic as you think, but you basically labeled it with a different color. So for that particular polymer, you tell him, take off your red shirt, blue shirt, put on the green one. So there's that piece of the deuterated chain, then you put it back into the normal polymer. Now you have a green and the blue matrix, so you can see it again. So that's how people measure it in the melt back in the 70s. And that's why this Paul Flory got a Nobel Prize, because he didn't even do experiment. He predicted that's going to happen, and later people confirmed it. That's the beauty about his simple theory. Yes, indeed, the polymers in the melt behave like idealized chain. Okay, so everything we talked about at the beginning, Gaussian coil, ignore these interactions. Actually, in the end, they have some real practical use. There's a lot of processing relevant to polymer in the melt, as you can see. So we finished the scaling relationship. We explained 3 different relationships. So that's pretty much summarize the last piece of lecture I want to deliver. So I'm going to use the next 10, 20 minutes to walk everybody back how we advanced from the first lecture to now. So, and I'll explain the significance and why we are doing this way. So if everybody recall, the whole chapter of 6 in Ting Lodge's textbook is trying to get everybody on board to understand how a single polymer chain in idealized case and real case would behave, right? So we are basically setting some stones, stepping stones for us to go for more advanced lectures in October and November. So what are these fundamentals? We need to know how does different polymer structure and molecular weight would behave structure-wise. Structure-wise, it means how they look in the 3-dimensional space. And in order to do that, if I tell you the scaling relationship, it's like I did. I believe at the beginning of the lecture, imagine how big a certain molecular weight of polyethylene. And I think by now everybody should have a good understanding how to read that and how to understand that. So we begin the lecture by showing everybody most simple model, the random walk to talk about Gaussian coil. So you need to know what is the definition of the Gaussian coil? How do we interpret the Gaussian coil, and why we want to start with something simple? Because it's omit many complex physics factors. It's straightforward. Almost every single person can understand. I can explain to my 5-year-old about random walk that is, right? So that's a good start to get everybody on speed to understand how end-to-end distance, because we don't want to talk RG at the beginning, so we use the end-to-end distance combined with the vector concept. We can help everybody understand what is end-to-end distance, dependence on your bond length, number of bonds. That's what we did in the first few lectures. We talked about simplest free joint chain to consider more complex form, free rotation chain, bond angle, etc. But in a nutshell, all those three models we talk is all called idealized chain. We never consider polymer-polymer interaction, so there's no expulsion force that is we discussed today. That is never considered. We only consider bond angle limitation. The bond angle do have an effect. Later on, we chatted about characteristic ratio, persistence length. All these are relevant to this bond angle because bond angle rigidify locally how your chain could be bending and moving. So you can see a more smaller angle resulting in the bond or resulting in a bigger characteristic ratio, make the bond more rigid. And we discussed, after that, we discussed about one-like chain model, which is something slightly different with all the three models we talk about because that's for semi-rigid chain. Up to that point, I think everything is more fundamental. So you need to understand those fundamental concepts. What is cone length? What is contour length? What is persistence length? How to define them, and how they are defined and used. And what is characteristic ratio, for example? All these are intertwined. After that, we actually now, in the later half of the class, we are trying to more bring back everybody from a very idealized world to a little more and more realistic world. First, we did a change from end-to-end distance to radius gyration because we talk about it's hard to measure end-to-end distance, but easy to measure RG. And we didn't talk about how to measure it. You guys will learn next class, next year. Next semester, Dr. Simon is going to teach you all about light scattering and how you use that to measure RG, what a Zim plot is, and all another area is dynamic light scattering, how to measure hydrodynamic radius. But we won't chat too much, assuming you will be able to take sample in solution, do light scattering, and get RG. So we have a way now to link abstract molecular weight end-to-end distance to something realistic we can measure. Some of the homework covered that. Give you molecular weight, give you the RG, and you can use those parameters to understand rigidity conformation. It's quite useful. After we talked about RG, then we did something is talking about distribution and probability. This one is a little bit tougher compared to everything we discussed at the beginning, because distribution is relevant to a single chain at the given time point. What's the chance of finding it? And the reason we need to talk about that is relevant to two important concepts. We need to use that concept to explain what the entropic spring and the attractive forces. And entropic spring will be touched again in November when we talk about rubber elasticity. There's a particular good reason why rubber is superior than metal springs when we need that rubbery response, okay? After we talked about this distribution, we then come into the last part is scaling concept. Then we discussed about what is the real chain and what's the difference with idealized chain. Okay, in the real chain, we do need to consider this a self-avoiding effect. And we just did it this morning to explain a little bit how you can use that to visualize how this expulsion force will impact your polymer coil. So that's kind of a grand picture what we have down. In the study, I suggest everybody, the homework is always going to be harder than the final, the exam. So I want everybody to spend a little bit of time to think about after class. So we're going to cover the homeworks. So some of the simple homework we certainly want everybody to master and can do. For example, how we can understand, based on light scattering experiment, molecular weight, how do we understand chain conformation? This is very simple. So I hope everybody can take a look at that one more time, understand how to relay those parameters. The other part I think very important is concept of radius gyration. I think everybody needs to dig into that, understand how the RG is being calculated, what is momentum of inertia, what is concept of how that impact your radius gyration. Okay. So with that, I think you should do well. What I'm looking for students in the test, I like to grade such that I want you to show detailed step how you are approaching the problem. In a numerical problem, don't worry too much about final numbers because it can be off by a little bit if you put in normal. But it needs to make physical sense. Okay, you should double check if you get persistence length is enormous high, then you should worry. Most of flexible polymer LP will be roughly within a few nanometer. Okay, it should not be like 0.1 angstrom or 20 nanometer. That doesn't make sense, right? So you do need that, but I'm looking for how you link to what we learned in class. So show your step in the answer. The other part I will be looking for is conceptually. You need to be able to make a conversation with your future employee about those concepts. So I want to make sure you follow all the detail about what is cone lenses, what the contour lens, what's the difference, etc. So we certainly want to make sure everybody knows that. Any question for me for this? Otherwise, I think we're going to take a look at the exam in 2 weeks, in 10 days, not 2 weeks, okay? Next week, we're going to go through homework. Then I can either do an office hour, let everybody study on Thursday, or if everybody feels good about homework, then we can maybe start the solution part. The next chapter will be more interesting and useful, I think, for the conformation of the chain. It's a little bit abstract. It helps you to understand size, but how size is useful and important will be covered more in the next lecture. Next part, in October, we're going to discuss the chapter 7 of Tim Lodge's textbook. And chapter 7 is all about polymer solution. So now we're going to move away from a lot of things we discussed, idealized chain. Idealized chain is basically a chain in a vacuum. No neighbor. You're like an astronaut being disconnected from your mothership, floating around by yourself. But in the solution, it's going to be different. Now you have solvents. Solvents going to interact with polymer. So we're going to learn all about a very important concept is called a phase diagram. How does polymer behave in solution? We're going to discuss all the detail about that. We're going to learn about Florey-Huggins parameter, how your polymer interact with another polymer. Will they mix or not? Will they phase separate or not? It's another important question because when likely in your future job you're doing, for example, you engineer a new plastic. Unlikely it will be just a single component. You need to formulation, you need to mix it. So it's a question, are they going to mix? Are they going to be homogeneous? They all can be explained in the polymer physics in the solution property, okay? So we're going to cover that in the next couple of class. We're going to try to cover everything in October for that one. So we're going to, in the next field lecture, we're going to go there. So for today's class, that will be it. Any question for me? If not, then good job, everybody. Then I'm looking forward to chat with you guys next week about homework. And make sure you hand in before we begin on the class, because I'm going to go through the question. And ideally, if you can hand me on Monday, then I can read it and I can give you feedback already. Okay? If you're already done, give it to me. I appreciate it as well. Yeah. You can leave it here. Let me.